Okay, thanks everyone. Thanks to the organizers for giving me this opportunity to talk, and thanks everyone for coming. So I'm going to talk about a project that we're going to work on in algebraic statistics related to Gaussian graphical models. At a high level, what is a Gaussian graphical model? This is a framework for constructing statistical models on groups of random variables, and a lot of times people think about looking at large collections of random variables. You use a graph to represent different types of interactions between those random variables, and there's lots of different types of edges you might use in the graph. You might have directed edges, bidirected edges, or just usual undirected edges, like we're thinking about in having graphs. And that graph structure is used to express relationships between the random variables in multiple ways. One of them is through conditional independence structures, and the other is the graph gives a parametric representation of the model. And I'll talk about both of those as we go along. For Gaussian random variables or normal random variables, the graph structure relates the random variables to each other through linear relationships. Okay, so let me just start with some very simple examples of how you might think about a graph structure relating random variables. So here's a very, very simplistic model. 3 random variables, which are a person's income level, the amount of processed foods they eat, and then whether or not they maintain a low cholesterol level. I added this, because my doctor's complaining about my cholesterol, so I added this example. So you might think about a graph structure relating those random variables where you use directed edges to express relationships, because how much money you make affects how much highly processed foods you're going to eat, which in turn affects your cholesterol levels. So it's very natural to think about a directed graph expressing causal relationships but affecting the structure of the random variables. Here's an example of a very large graph structure relating random variables. So this is a gene interaction network where in the particular study that people were doing here, they were trying to predict susceptibility to the COVID virus by looking at gene interactions and how other diseases were affected by the presence or the different alleles you had for different genes. So it doesn't really matter. We're not going to talk about this in too much detail, but the point is you can have a large graph expressing relationships, and this is a situation where maybe the graph is not expressing causal relationships. We're just doing like exploratory data analysis where we want to uncover this graph structure to understand which gene should I focus my targeted study on by understanding which things are interacting with each other. Okay. So I'm going to talk about graphical models with Gaussian random variables. And so what does that mean? So a random vector, an m-dimensional random vector, is a multivariate normal random variable, or Gaussian, with mean mu and covariance matrix sigma. That means that the density function for x, in terms of these parameters mu and sigma, is given by this very this pointer is hard to use. This complicated density function. Okay, so it depends on mu is appearing there and sigma is appearing there through sigma inverse. Okay, we use the shorthand to say that x is distributed as a normal mu sigma random variable. What does this look like if I graph this density function? Here's where m is 2. The density function, it has a peak at mu, and then it dies away exponentially fast from that. It has elliptical contours because we're looking at a quadratic form here, and the major and minor axes of those ellipses are related to the structure of the positive definite matrix sigma. okay? And here is like scatter plots of Gaussian random variables for different values of sigma. And so that sigma can be used to represent like a negative correlation here. So if the kind of off diagonal entry in this 2 by 2 matrix is negative, it's going to look like this. Here's a situation where the two coordinates x1 and x2 are like pretty much independent of each other. So you're getting like almost circular contours. And then you have like positive correlation where the off diagonal entry are positive. Okay, so that's some structure about what a multivariate Gaussian is. Here's how the undirected Gaussian graphical models look. So essentially, we're going to put some structure on the covariance matrix sigma that's determined by the structure of a graph. So we start with a graph G. It has vertices, which are the numbers 1 through m. It has an edge set. And we're going to look at this set of this linear space of positive definite matrices. So we take positive definite matrices K, and we're just going to require that an off diagonal entry must be 0 if I to j is not an edge in the graph. So the missing edges in the graph tell me where the zeros are in this matrix K. And the Gaussian graphical model associated to this graph is going to be all of these normal random variables where the sigma is restricted to live not in LG, but in the inverse space of LG. So I'm going to take that linear space LG. The inverse means I'm going to take all the sigmas I get by doing the inverse of the matrices in LG. No, we'll always have the diagonal. Okay, so this, again, this was only about the off diagonal entries. Okay. Okay, so as an example, so if I have this graph on 4 vertices, this 4 cycle, the matrices that I'm looking at here will have zeros in the 1, 3 and the 2, 4 position because there's no edge. There's no edge from 1 to 3, and there's no edge from 2 to 4. But otherwise, besides being a symmetric matrix, it's an arbitrary matrix, and I guess it needs to be a positive definite matrix as well. Okay. And so the Gaussian graphical model is going to say, take all the linear space of all matrices like this and take the inverses of all of those matrices. And that's the set of positive definite matrices I want to look at. Okay, so as commutative algebra people, the first thing you might ask then about this model is to say, okay, well, I have this space. It's a semi-algebraic set because I'm looking in the cone of positive definite matrices, but let's not worry about the that semi-algebraic structure. Let's just look at the algebraic variety that we get. So let's take the Zariski closure of this set. And so the first thing you could ask is just what is the vanishing ideal of this set? Okay, so we're going to look at the set IG. That's the vanishing ideal of this inverse space, the covariance matrices. So that's sitting inside of this polynomial ring in the entries of our symmetric matrix sigma. And that's going to be, I'm going to take all polynomials that evaluate to 0 for every covariance matrix that lies in this inverse space. And so just like the fundamental question you can ask when you're presented with the new family of algebraic varieties is to just say, well, what can we describe what the vanishing ideals are for every single graph? Okay. And maybe we want to know more, like what are the Grosvenor bases of these ideals look like? What other kinds of like commutative algebra invariants we can study about these things? Okay, so again, for our 4 cycle, again, we're looking at the inverses of these matrices with this structure. And you go to your favorite commutative algebra package and compute the vanishing ideal, and you find that it is a complete intersection. It's generated by two determinantal cubics, and they're obtained by looking at specific 3x3 submatrices of the covariance matrix. So one of them is you take the you take your covariance matrix, which is a 4x4 matrix, and you're going to look at the submatrix where you do rows 1, 2, and 4, and columns 2, 3, and 4. Take the determinant of that 3x3 matrix. And then the other generator is you look at columns 1, 2, and 3. No, rows 1, 2, and 3, and columns 1, 3, and 4. Take the determinant of that. And those are the generators of this ideal. And, you know, we commutative algebra people love determinants, determinantal ideals. So it's a great like playground for thinking about commutative algebra questions.
Does it come out to be like the missing edges? So like in the first one, you're missing 3, 1, and the second one, you're missing 4, 2, right?
In this one, it's exactly that, yes. But the structure can be much more complicated than that. But in this one, it is exactly that. Okay, I'll talk about that in a little bit as I get into describing the equations a little bit. Okay, yeah, so it turns out that statisticians know lots of equations that belong to these ideals, though they wouldn't say it like we know a lot of equations that belong to these vanishing ideals. But they do know a lot of structure about these that turns into commutative algebra structure. And that structure is through conditional independence structures. So have you never seen, I'm sure you've seen independence in, you know, your basic undergrad probability class before, but maybe you've never seen conditional dependence. So let me just describe what that is here. So two random variables x and y are said to be independent, which is denoted by this x like double perp y. If the probabilities satisfy this formula, the probability that x is less than or equal to little x, given that y is less than or equal to little y, is just equal to the probability that x is less than or equal to x. Okay. And x and y are conditionally independent given z if essentially the same thing happens but conditioned on z. So that is the probability that x is less than or equal to x given that you condition on y and z is just the probability that x is less than or equal to x given z. Okay. You may have seen, you've probably seen independence given more as like a product formula. The probability of x and y is equal to the probability of x times the probability of y. But to me, these expressions are more intuitive because of the like explanatory way of thinking about independence. So these formulas for independence and conditional independence translate into the following, you know, in layman's terms. If x is independent of y, knowing the value of y doesn't give you any information about x. Okay. And conditional independence, the same thing, but conditioned on z. So for each value of z, knowing the value of y doesn't give you any extra information about x. Okay. So if you want to think about, you know, can a variable help you predict information about another variable? Well, if they're independent, it can't help you predict anything. You want to use variables to help you predict values of other variables. You want things that are like highly dependent with each other. Okay. And that's what a lot of times statistics is about, even though sometimes, you know, we phrase doing hypothesis tests and things like that as like trying to see if things are independent of each other or not. A lot of times we want to know that they're not independent so that we can use them to make predictions. Okay. Anyways, here's a basic example of kind of showing the idea of conditional independence, again, in this very like simplistic example of a graphical model of a graph from earlier. So again, this wealth versus health relationship. So income level, amount of processed foods eaten, and whether or not you maintain a low cholesterol level. So we know just intuitively, and there's tons of data about this, that people that make more money tend to be healthier. Okay. But there's not a direct, so those things are not independent of each other, right? Because of that, you make more money, you tend to be healthier. But they're not directly have a causal relationship with each other, right? Because there's these intervening things. If you make more money, that leads to different behaviors that then lead to you having a lower cholesterol level or access to better healthcare or whatever. Okay, so this is a situation where X1 and X3, they're not independent of each other, but in this very simplistic model, they're conditionally independent given the intervening variable 2. Okay, in practice, really, income and cholesterol level are going to be conditionally dependent given probably a whole bunch of other intervening things. But in the simplistic model, just that one in the middle. Okay, so that is conditioned on whether or not you're eating a lot of processed foods. Knowing the income level doesn't affect our estimation of whether or not you have a low or high cholesterol. Okay. 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 So we had this, notion of conditional dependence. Maybe you don't like probability and it makes you uncomfortable. That's fine because conditional independence is about determinantal ideals, at least for Gaussian random variables. So what does this look like? So again, we have X, which is distributed as a normal mu sigma random variable. And let's take 3 subsets, A, B, and C. So the conditional independence statement, A independent of B given C. By what I mean by that, I should have put this on the slides. What I mean by that is that the random variable X is independent of the random variable B given the random variable XC. Okay, so I'll use the shorthand A independent of B given C for that. So that holds for a normal random variable if and only if you look at this submatrix of the covariance matrix whose rows are indexed by A union C and whose columns are indexed by B union C, and the rank of that matrix should be equal to the cardinality of C. Okay. Okay, so as an example, I'm talking about X1 independent of X2 and X5 given X4 and X6. What I'm supposed to do is I'm supposed to look at the submatrix where I do row indices 1, 4, 6 and column indices 2, 4, 5, 6. And the rank of that submatrix is supposed to be equal to 2. It cannot be less than 2. And I indicated in blue here, there's a principal 2x2 submatrix that comes from the things you're conditioning on. That submatrix has to have rank 2 because you're talking about a positive definite matrix. So this matrix can't have rank less than 2, and we're saying it has to have rank exactly equal to 2 when we have conditional dependence. Okay, so we can make an ideal associated to this independence statement, which is the conditional dependence ideal. So we just take that particular submatrix of our covariance matrix, and we do all of the C+1 minors of that. That is going to encode this rank condition. Okay. Okay, so conditional dependence for Gaussian random variables is just, determinantal constraints. Great. And for graphical models, it's well understood how the graph structure gives you conditional independence structures in terms of just basic combinatorial structures of the graph. So if you have your graph G and you have disjoint subsets A, B, and C of the vertex set, then we say that the set C separates the sets A and B if every path from some A and A to some B and B has to pass through some C in C. Okay, so in this graph here, the set 2 and 4 separates 1 from 3 because every path from 1 to 3 has to hit some element in C, 2 and 4. Okay, so in a Gaussian graphical model, so I stated this proposition just for Gaussian graphical models, but actually is true for any graphical model. But since we're only talking about Gaussians, I just stated it this way. If you have a graph and disjoint subsets A, B, and C of the vertex set, this conditional independence statement, A independent of B given C, holds for all probability distributions in the graphical model if and only if C separates A and B in the graph. So this separation we have in this graph is going to tell me that 1 is independent of 3 given 2 and 4 in this graph. Okay. Okay, so okay, since we know that the graph gives us all of these conditional independences, that in turn tells us a whole bunch of determinantal equations that belong to the vanishing ideal of the model. Okay, so we can take a graph that n is supposed to be an m. We can essentially make the conditional independence ideal associated to the graph. That is, it's going to be the ideal generated by all C+1 minors of the appropriate submatrices of the covariance matrix where A, B, and C range over all sets where C separates A and B in the graph. That ideal is called the conditional independence ideal of the graph. And those equations vanish on all of these covariance matrices that are in this LG inverse. So those equations belong to the vanishing ideal. And actually, they're a really good set of the vanishing ideal because on the positive definite cone, the variety that the conditional independence ideal gives actually is the same as the variety of the vanishing ideal. So in the kind of part of M-choose, and in the part of the space of symmetric matrices that we care about, the conditional independence ideal actually does define the model. But now we might ask again the commutative algebra question. Well, okay, so that's like in some kind of small region of the space of symmetric matrices. But is it actually equal to the ideal? Is the conditional independence ideal equal to the vanishing ideal? And what I'll tell you about in the next few slides, there's a number of situations where we do know that that's true, but it's a pretty open problem to answer this in general for most structures of graphs. And it's definitely not true in general for all graphs that that the conditional independence ideal actually equals the vanishing ideal for all graphs. So there's a lot to understand in this area, just in terms of what these ideals look like, even though you have this nice set of generators that kind of defines the variety, in the region where you might, where you're most interested in. It seems like it can be, far away from the actual generating set of the vanishing ideal in general. Okay, here's an example that we've seen a few times. If I take the 4-cycle graph, the conditional independence ideal. Okay, there's 2 conditional independence statements here that Hal noticed before I even talked about conditional independence, which is 1 and 3 are independent given 2 and 4 because 1 is separated from 3 given 2 and 4, and 2 and 4 are independent given 1 and 3 because 2 and 4 are separated given the set 1 and 3. And so those each give me 1 3x3 minor. So like this one here corresponds to the 1 independent of 3 given 2 and 4. This one here corresponds to the 2 independent of 4 given 1 and 3. Goodness. Okay, and the conditional independence ideal does equal the vanishing ideal in that case. Okay, so the case of cycles, that case was sort of recently done by Connor Hahn and Mateos. I'll just say his first name. Okay, he's not here. Okay, so I can butcher his name. Okay, you all know Mateos. Okay, so for cycles, it's true for cycles that the vanishing ideal of the Gaussian graphical model associated to a cycle is equal to the conditional independence ideal, in particular for, once you have, so the 3 cycle is boring, there's no generators, it's just a 0 ideal. But for 4 cycles, you're getting that the ideal is generated by determinantal polynomials of degree 3. That's because in a cycle, like every interesting separating set is going to have 2 elements. So it's going to be a conditional independence of a set from another set given a set of size 2, because that's what you need to like slice the cycle in half to disconnect it. So you're going to get a bunch of 3 by 3 minors in that case. And the proof of this is actually pretty hard. It uses this theory of the type intersection theory on the space of complete quadrics they wrote a whole paper, I think, with different co-authors just to determine the degree of this ideal. And then the second paper says, okay, let's like compute a Grobner basis of the conditional independence ideal, and then see that that ideal is radical and that it has the right degree. And then you deduce that the 2 things are equal because of that. Okay, so it's a pretty difficult proof. So cycles, we understand that completely. Let me give you some other examples where we know things where the conditional independence ideal equals the vanishing ideal of the graph. So I'm going to call a graph a fat path graph if it has the following property. So whenever you have an edge from I to j, you also have every edge k to l where k and l fit between I and j. Okay, so here's an example of a fat path. So why is it called a fat path? Well, you have a path that goes from 1 to 5, and then like you're allowed other edges like 2 to 4, but then you have to have like 2 and 3 has to be there, and 3 and 4 has to be there. So this condition means you're always going to have the edges 1 through 5, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and then there might be some other edges. What does K look like when you have this fat path structure? It's going to be like this, ladder structure for people who do determinantal ideals. So like all of the 0 entries are like shoved into the upper right corner, and then because it's symmetric in the lower left corner as well. Okay, so if the graph has this structure, then it turns out that the vanishing ideal is equal to the conditional independence ideal. And again, this is also kind of a hard proof because it uses the fact that in this special case, the vanishing ideal is the same as the vanishing ideal of some symmetric version of matrix Schubert varieties for people that like those kind of determinantal ideals. Okay, so the structure here that's really nice is that the determinants you get are always determinants that are like maybe I'll draw something on the board. Like you have your covariance matrix. In this kind of case, you're always looking at submatrices that are like these upper right submatrices, and you take all of the whatever C+1 minors in those submatrices. And you have lots of like overlapping sets like that where you get these determinantal constraints. Okay, so it's a really nice combinatorially structured set. And that was joint work with Alex Fink and Jenna Reichstadt, who I saw Alex here, and Jenna. No. Okay. Well, I thought she was maybe going to be here. Okay. Okay. New baby. Okay. New baby. Okay. Can't keep track of all the babies. Okay. 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 And then one more case, and it's sort of the case that I think our group is going to focus on looking at more details about this case, open. So we'll probably look at lots of things as well, but I think this case is a good starting point for getting into these projects. And that is the case of graphs that are called block graphs. A graph is called a block graph if it can be obtained from complete graphs by gluing them together, but just at single vertices. So this graph is an example of a block graph. So like here I have a complete graph, and then I glued that together at this complete graph just at the vertex 3, which I then glued that to this complete graph at the vertex 4, and then et cetera. Okay, so just gluing them together, but just at single vertices. So in a block graph, when you're looking at these separation conditions, they're always going to have the kind of most interesting ones. You can always just choose a separating set of size 1. Okay, so like if I take the vertex 6, then all of these guys on this side, 1, 2, 3, 4, 5, 7, are separated from 8, 9, 10, and 11. Okay, so every separating set from a conditional dependence is going to look like A independent of B given a singleton. And so in terms of these rank conditions, that case is going to correspond to just looking at 2 by 2 minors only. Okay, so what that means then is the conditional dependence ideal is going to be a binomial ideal. So this is a case where people that like toric ideals, like me, can do say interesting things about this case. So the conditional dependence ideal will be a binomial ideal in this case, and then of course the natural question to ask is, well, is it equal to IG? In which case it will be a toric ideal. Okay, and so that's true. So with my former student Pratik, we showed the following things. So the following conditions are equivalent on a connected graph. G is a block graph. The vanishing ideal of the Gaussian graphical model is a toric ideal. And the vanishing ideal of the Gaussian graphical model is generated by polynomials of degree less than or equal to 2. And furthermore, in that case, the vanishing ideal is equal to the conditional dependence ideal. But and again, the proof was hard, but maybe not as hard as the previous theorems. But there's just like a lot of combinatorics to go through with proving that these binomials actually generate the ideal. But we weren't able to show, and it seems like it should be an easy thing to do, but we just weren't able to do it, that those degree 2 generators actually are Grobner basis for this ideal. But then there's lots of other questions you can ask. Like once you're in the toric case, you have all these tools from polyhedral geometry that should be helpful to understand this case better. So there's an associated polytope or polyhedral cone associated to this variety. Like, what can we say about that? How can that help us answer questions about the polyhedral structure, about the algebraic structure of these varieties? Like, what's the Hilbert series look like? There should be a lot of interesting combinatorics there. Even simpler, just like what is the degree? Can we get an answer to what the degree is without going through all of the hard intersection theory of the space of complete quadrics? Maybe we can say whether or not these things are Cohen-Macaulay. Probably they are. Yeah.
Because of the simple fluid condition, can you do some kind of Meyer-Torres thing with fluid? I mean, you're doing it right. Because the intersections are so simple. I mean, you're doing along a single vertex. You can imagine doing some kind of.
That's a great problem for the students to work on. Yeah, maybe. Okay. Okay. So actually, I like this example. It's sort of like it's a weird thing that these things are toric actually, because these models all have a natural parameterization, which is to take this K matrix and invert it. That actually gives you a parameterization. This is a block graph, so I'm supposed to get something toric, but the natural parameterization is not a monomial parameterization, right? Here's a example for this little block graph. Again, if I invert the matrix K, just using the usual like the classical adjoint formula for the inverse, these are the formulas you get, and like those aren't monomials. So what's going on? Like, why is it coming out to be toric in this case? And it turns out that there's a different parameterization you can give that is a monomial. And it's related to the structure of these block graphs. Block graphs are the graphs that have geodesics, essentially. They have a unique locally shortest path connecting any pair of vertices. So they're kind of the natural generalizations of trees with respect to that property. Okay, so there's, in a block graph, there's a unique locally shortest path connecting any pair of vertices. And this parameterization, this monomial parameterization is the one that gives you the toric structure, which is you're going to map sigma ij to a monomial that is the product of the edges along the unique shortest path. And then, then you have these ai times aj that you just need there to keep track of the multi-grading, essentially. Pardon? It's a geodesic, so you can't like perturb it so that it becomes shorter. Okay, so like for example, a cycle has two locally shortest paths that connect any pair of vertices, but does not in general have a single unique shortest path that connects any pair of vertices. Okay, does that make sense? No. Yeah, say it's that. Okay. Okay. So how does the proof go for this? So again, it's a little roundabout. So you look specifically at the shortest path map, show that it's generated by quadrics, and that those quadrics are the same as the quadrics from the conditional independence structure. And then again, you use the fact that these two ideals, the shortest path ideal and the vanishing ideal of the model, they're both prime, they have the same dimension, so they have to be the same. And so, one thing that's really interesting here is that, okay, we have this sort of non-monomial parameterization, and then there's also this monomial parameterization that gives the same thing. How are they related to each other? Well, actually, the shortest path map is kind of like a toric degeneration of the of itself. Yeah, it's weird. If you look at certain, there's a term order on the k variables where the leading terms are the shortest paths. Okay, so it's like these polynomials are a Sogby basis for the ring that they generate, but yeah, it has this weird thing that, like, for people who study Sogby bases, usually there's a toric ideal associated to the vanishing ideal, those initial ideals. It just happens that it's the exact same ideal as the ideal that you started with. It's this very weird. Never seen anything quite like that before for Sogby bases. Okay. Okay, so in the last 2 minutes, let me just say, like, what are the problems then that the group working on this will we kind of start to think about to work about? So we want to, again, study the toric geometry of this shortest path ideal. And again, there's lots of questions we can ask. Can we find Grobner bases? What about basic other commutative algebra properties like normality, Cohen-Macaulay? Can we, when is it Gorenstein? Whatever. Can we get at the combinatorics of like the Hilbert series, the Earhart series of in this case? But then I think there's interesting questions like, okay, you could try to come up with a shortest path degeneration of your of your parameterization like this, even if it's not a block graph. Does that give you anything useful for these vanishing ideals? Maybe something nice happens there. Okay, the graphs that we understand the vanishing ideals so far, it's pretty limited. They're these block graphs, fat path graphs, which aren't super complicated, and cycles. Can we do anything to extend beyond that? Like maybe just graphs that have one cycle plus some other like edges hanging off. Can we even get at that case, which should be generated by equations of degree 3 and 2, but I don't know. And then, of course, there's the big question, which I didn't talk about at all at this point, which is there are non-determinantal equations that live in these vanishing ideals. You have to get to relatively larger graphs before you start seeing them. So for example, for this graph with 7 vertices, it turns out that among the like 100 generators of the vanishing ideal, there's one of degree 5 that is not determinantal, and it's this beautiful equation with 12 terms that's called a pentad that was discovered by statisticians, and it's related to determinants in some way, and it has, it's like the sum over all 5 cycles with certain signs. So it has like really interesting combinatorics. Like, what kind of generalizations can we make? Can we understand when those sorts of things arise? Determinantal equations are among the generators, but you might need more generators. Uh-huh. It is correct, yeah. Only in the positive definite cone.
I see. So even the naive description of the geometric object is
Even the naive. Yeah, I mean.
Because I thought we're talking about rankless.
Yeah, in the positive definite cone. So like for example, you need this equation if you want to understand points on the boundary of the positive definite cone that are like limits of things that are in the positive definite cone. Like, you have to have this equation there to understand like even the closure of the semi-algebraic set that you start with.
So is there something like a Fluffy or
No.
Where
No, you can get it from determinants by doing a resultant between 2 determinants, but by eliminating a variable with 2 overlapping determinants. But yeah. But yeah, the question is to try to understand better where these sorts of things come from, what these equations look like, or generalizations of them. For what graphs do you need things like this? I don't know. Okay. So let me just summarize what I tried to tell you in this talk. So first of all, the vanishing ideals of undirected Gaussian graphical models, they're pretty difficult to describe. We know some cases the proofs are challenging in all of these cases. Big open question, again, to understand for which graphs the ideals are generated by just these determinantal conditional dependence constraints. It's true for these categories: block graphs, fat path graphs, cycles, but there are many open problems that remain. And I'm over time, I think, and I will stop here. Well, I want to stop anyways. So thank you for your attention.